This is my first attempt of uh, recording a video. Uh, Unfortunately, I won't be able to draw anything, so I just open the slides I already prepared for you, and I'll go through them, and I'll make a commentary in the hope that you will understand the stuff. And of course, I have to think about other modes of teaching later on. So, just to refresh your memory, our last lecture started with something like that, and let me just take you to the point where we ended the lecture. So we ended the lecture with Bernoulli random variable. Before that, this Dirac distribution was introduced. But I would like to go back to the Iverion bracket because I want to refresh all these different notations in a way that you follow it without me doing everything on board. So this was actually a carefully thought exercise. So let me recall what we meant by the Iverion bracket. You just have any proposition, say x belongs to B. So this proposition will either be true or false. Remember this small x, Actually, I should have been, focusing on that part, because there is this square bracket if you see. So you have a proposition inside a square bracket, and when the proposition is true, the square bracket will turn it into a 1, and if it is false, the square bracket will turn it into a 0. On the other hand, when we are talking about a random variable, we can come across a similar scenario. So in this case, I don't know why it's not working. So if I write something like that, which involves the random variable x, what I actually mean is the pre-image of a set. So if I have a set B on the real line, I want to know what is the pre-image or the inverse of that set B. Remember, x has taken points from the original sample space to the real line, so x inverse is now taking a set of points back to the event space. So mathematically accurate notation is x inverse of B, and also remember this square bracket, so that we know that we are talking about sets and not points. And that x inverse will also give you a set. A more practical notation is actually an abuse of notation, where you simply say x belongs to B. But notice the difference. X belongs to B will give me an event when x is a random variable, but this small x belongs to B in the bracket will give me a Boolean variable, a 1 or a 0. So let's connect these two different ideas. into something very new. And that is what I mean by this Iverion-like bracket. So say I take this logical statement from the Iverion bracket, yeah, and I want to do something with it so that it returns me a set, not a number, either 1 or 0, but I want a set which is either the sure event, the full sample space, or the null event. Remember, if you want to have a correspondence between logic and set theory, in logic you say something is true or false, and in set theory you have sets. So okay, the true definitely corresponds to the full sample space or the sure event, yeah. So remember, the true corresponds to the full sample space and the false corresponds to the null event or the impossible event. So now if we replace that square bracket with this middle bracket here, yeah, this one, and I put the same proposition, any proposition s of x, or any statement s of x. S stands for statement. I have a logical statement. If that logical statement is true, yeah, this new bracket, which I call the Iverion-like bracket, will give me the full sample space, and you know that sample space corresponds to 1 or true. If it is true, if this statement is true. If the statement is false, I will get an empty set. Now you must be thinking, why, what is the big deal? So you will see later on that this will simplify long expressions that involve set unions. Remember, this simplification we have seen when writing normal mathematical expressions. Yeah. So the Iverion bracket simplifies a lot of algebraic manipulations. So we want the same simplification when we write unions, set unions. So if you remember, the Iverion bracket kind of filtered expressions, yeah. So if something was true, that expression would be included in the summation, and if a statement is false, the Iverion bracket will actually get rid of that. So it will turn a whole bunch of an equation to 0. So let's try something like that. So we want to filter events by intersecting them with the Iverion bracket. So let's say I have a set union in which this A has to appear, but I want this A to appear conditionally based on some statement. If that statement is true, remember what will happen. This new Iverion-like bracket will turn that logical statement into the sample space. Now A intersection sample space will give me A, yeah. But if that is false, the Iverion bracket, the Iverion-like bracket rather, will give me an empty set, and A intersection empty set will be empty set. Now remember, in a set union, if you see empty set, you simply ignore it because it will not change the rest of the expression. So this is how you can filter A by the Iverion bracket. So let's see. And there is an interesting analogy, because we know true has a mapping with the sample space and false has a mapping with the empty set. The probability now connects these two brackets. So if I apply the probability measure, to the Everson bracket, yeah, applied to some logical statement, this probability will either be a 1 or a 0 depending on whether this is true or false. So it actually gives me the Everson bracket. So you can now just read this out loud to see the connection. Yeah, the probability of the Iverion-like bracket, yeah, equals the Everson bracket itself. Now there is even more to that. We observed in previous lectures that you can recall the independence of events. Yeah. So if you remember, two events are independent if the intersection of those events, the probability of the intersection is the product of probabilities. Now if you apply this rule to the null event, yeah, the null event is independent of any other event. Similarly, if you apply that to the sure event is also independent of any other event, which means that if I take intersection of A with the Everson bracket, this Everson bracket will either be the empty set, in which case it will be independent of A, or this Everson bracket will be the sample space. The sample space is also independent of any other event. So either way, whether S of x is true or false, this intersection, the probability of this intersection will be the product of the probabilities, So the probability of A is the probability of A, and the probability of the Everson bracket is the Everson bracket. Now this equation, which looks very unusual because you may not be used to this, but remember, this is very, very useful. We will see this in the topics to come. So let's start again with the Dirac measure, or Dirac distribution. Why do I start with this? Is that this is the simplest thing you can imagine. It's not even a random variable. Mathematically, it does qualify for a random variable, but actually it is not. So say you have a probability space, of course, with some sample space and some event space and a probability measure. Now that event space, if you keep that as small as possible, the smallest event space possible, the smallest collection of events, which is that? The empty set and the sample space. I don't think you can have an event space smaller than that. And just take the usual probability measure. Okay, so if I want to define a random variable x on this probability space, or for this probability problem, because you see this must correspond to a problem, because I only have two events in the event space, this random variable must assign a single value to all the points in the sample space, because the sample space is the event which is non-empty. That's the only event. So let's say that we assign a value a to all points of the sample space. So I'll simply say x of any point in the sample space is a, and yeah, that's it. There is no and, because any point in the sample space is assigned the value a. So now I want to know, I have a random variable and I want to know its probability distribution. So for that I just take any Borel set on the real line. You remember, on the real line I can imagine any set with certain properties which we already discussed. So open interval, closed interval, open, close, half open, all those different types. You can imagine any subset, so on the real line. So what we do, I would like to express that set, yeah, as a disjoint union. So remember, A is the key here. So this B will either have an intersection with A or it won't have an intersection with A. So I can just decompose this B into two events. Yeah? B intersected with that set, single element set, and B without it. So what will be the pre-image of this? Yeah? X inverse of B. It turns out that this answer will depend on whether B includes A or not. So if B includes A, you will get the full sample space, yeah? Because you know A is the value assigned by X to all the sample points. But if B does not include A, then the answer has to be empty set, because there is no point in the sample space which was not assigned by X. So you see, because this concept of Iverion-like bracket is new to you, I just reproduce its definition there. But you should know what I mean by this. So now we want to know the probability of this. Actually, we want the probability of B. But because B is on the real line, I can only apply the new measure, the Px. I cannot apply P to B. So Px is the measure or probability measure which is available on the real line. But I can translate that to the original probability measure applied to this pre-image, yeah? And that gives me the probability measure. So now I have everything. If I have it, and this is what we mean by the Dirac measure. Yeah? So the probability measure of this random variable, which is actually a deterministic random variable because there is no randomness involved. You see, this is a deterministic random variable. The probability measure of this random variable, deterministic random variable, is given the name Dirac measure. Yeah. Why it's Dirac? Because it is centered at a single point. Yeah. We can even have a notation for that, delta with a subscript A. Delta with a subscript A, when you see this as a probability measure, what it does is that if you apply it to B, we simply borrow it from that, yeah? So the Dirac measure of a set will give me 1 if that set includes the point of definition. Otherwise, I'll get a 0. So now I can summarize everything. Yeah? The support or countable set, which has only a single point, the strictly positive PDF, remember the discrete PDF, which is 1 because that's the only value. All the probability is concentrated at a single point, and the CDF is also 1. I mean, not the CDF, but the strictly increasing CDF. You know all these terminologies. The actual PDF and CDF, of course, discrete PDF, can be recovered from this. So we are now done with the Dirac measure. Okay, let's move on to another important point, is that we chose A as a particular value, but this value can be chosen anywhere on the real line. Yeah. So you cannot tie the definition of Dirac distribution to a single value of A. In fact, each value of A will give you a new distribution. So it's more appropriate to speak of a family of distributions. So we have the Dirac family of distributions, and that is the set of all distributions um, for each value of a. So delta a is the distribution for particular value of a, and that a as a parameter can take any real value. So we have a Dirac family of distributions. We'll see this concept